Hello and welcome. I am very glad that you have found your way here to this quiet corner of the internet. Tonight's journey is designed for you. There is nothing left to do. The day is over. The tasks are finished. The world outside is winding down, and here in this space we have nowhere to go but outward, into the dark, into the deep velvet silence of space. Tonight we are not simply stargazing. We are not merely looking up at the pinpricks of light that decorate our night sky. Instead, we are going to drift slowly and gently through our own home, the Milky Way. It is a vast spiral, a colossal wheel, composed of stars and dust and strange, invisible matter. It has been turning slowly, majestically, in the vacuum of space for over 13 billion years. It is a structure so immense that light itself, moving at the fastest speed in the universe, takes 100,000 years just to cross it. But beneath its beauty, beneath that glowing band that stretches across our summer skies, lie secrets. There are rogue stars wandering alone in the dark. There are invisible forces holding the spiral arms together. And there are ancient remains, fossils of light, that defy what we thought we knew about the cosmos. We will travel gently from the outer, gossamer edges of its spiral arms, deep into its secretive, hidden core. We will witness colossal collisions that happen so slowly they look like stillness. We will find stars older than the galaxy itself, burning quietly in the halo. You will hear of black holes and stellar nurseries and the strange, unfinished story of a galaxy that is still growing, still evolving even as we sleep. So, let us begin. Let us drift upward away from the solid ground into the ocean of night. The Milky Way appears to us as a stable home. When we look up, we see the same constellations that our ancestors saw. The stars seem fixed. The band of the Milky Way seems permanent, a diamond river frozen in the sky. But this stability is an illusion created by the shortness of our lives. In truth, the galaxy is a place of constant, slow motion violence. It is built quite literally from the wreckage of others. Our galaxy is a consumer. Over billions of years, the Milky Way has encountered, captured, and absorbed smaller galaxies. It draws them in with its immense gravity. It unravels them like a thread being pulled from a sweater. It scatters their stars into long, tidal streams that wrap around the galactic disk like ribbons. One such galaxy is known as the Sagittarius Dwarf. It is a small, elliptical galaxy that ventured too close to our own. Right now, at this very moment, it is being pulled apart. It is struggling against the tidal forces of the Milky Way, but it is losing. Its stars are being stripped away, one by one, joining the vast population of our own halo. It is a slow cosmic digestion, a merger that takes aeons to complete. But the Milky Way is not done. Far off, in the deep night sky, there is a faint smudge, a blur barely visible to the naked eye. This is Andromeda, our great sister spiral. She lies over 2.5 million light years away, a distance so vast it is hard to imagine. But she is drifting slowly, steadily closer to us. Every second she draws nearer. Every hour, the gap shrinks by thousands of kilometers. In about 4.5 billion years, these two great spirals, the Milky Way and Andromeda, will meet. They will merge in a colossal cosmic collision. But the word collision is perhaps too harsh, too violent for what will actually occur. Galaxies are mostly empty space. The distance between stars is so great that when galaxies crash, the stars themselves almost never hit each other. They slip past one another like sand grains in a windstorm. Instead of a crash, it will be a dance. A gravitational waltz played out over billions of years. Gravity will pull the spirals apart. It will warp them. It will stretch them into long, sweeping arcs of blue and gold light. The familiar shape of the Milky Way will change forever. It will fold and twist, eventually settling down into a new form. A vast, elliptical galaxy, quiet and round and deep. Even galaxies are not eternal. They evolve, they collide, and they begin again. It is a reminder that everything on the grandest scales is fluid, like water, like time. But let us look back before we look forward. Let us look at the ancient history hidden in the dark. Because some stars in the Milky Way are older than the Milky Way itself. This sounds like a paradox, like a riddle. How can a part be older than the whole? The answer lies in how the galaxy was assembled. Not every star that shines in our sky was born here. Some stars are immigrants, some are wanderers. We find them mostly in the halo. The halo is a vast, spherical region that surrounds the flat disk of the galaxy. It is a lonely place, far from the crowded, bright spiral arms. Here we find stars that are ancient. They are known as metal poor stars. In the language of astronomy, metals are any elements heavier than helium. Carbon, oxygen, iron, gold. These heavy elements are created inside stars and scattered when those stars die. Therefore, a star that has lots of heavy elements must have been born recently, born from clouds that were already enriched by previous generations. But these halo stars, they have almost no heavy elements. Their chemical fingerprints are nearly pure, hydrogen and helium. This tells us they were born very, very early, shortly after the Big Bang, long before the Milky Way had flattened into a spiral, long before the disk had formed. Astronomers believe these stars originated in smaller primordial galaxies, tiny clumps of matter that formed in the early universe. These small clans of stars merged together billions of years ago to begin building the Milky Way. These stars are the survivors. They move slowly, high above the galactic plane. They travel in long, tilted orbits, diving down through the disk and soaring back out into the dark. They are like elder spirits, ghosts from a time before spirals, before order, before the galaxy knew what it was. In their pale, ancient light, we see a universe that was younger, wilder, and still learning to become what it is today. Now, let us bring our focus closer to home, to our own position within this vast structure. We often feel that the Earth is still. We sit in our chairs. We lie in our beds. The ground beneath us feels solid, unmoving. But this too is an illusion. Everything is in motion, quietly, endlessly. Our planet spins on its axis. It orbits the sun. But the sun itself is not stationary. Our entire solar system, the sun, the planets, the asteroids, and the comets, is moving. We are orbiting the center of the Milky Way at a tremendous speed. We are racing through space at over 828,000 kilometers per hour. That is more than 230 kilometers every single second. Imagine that. In the time it took you to hear this sentence, we have traveled hundreds of kilometers through the void. We are drifting through the arm of the galaxy. And yet, the galaxy is so vast so incomprehensibly wide, that even at this blistering speed, it takes an eternity to complete just one loop. One single orbit around the galactic center takes about 225 million years. Astronomers call this period a galactic year. It is the calendar of the cosmos. Measured in this way, our solar system is young. In Earth time, the Sun is 4.5 billion years old. But in galactic years, we have only gone around the Milky Way about 20 times since the Sun was born. Think about where we were during the last orbit. One galactic year ago, dinosaurs were just beginning to appear on the Earth. The continents were shaped differently, clustered together in the great landmass of Pangaea. The flowers had not yet evolved. The Atlantic Ocean was just a rift. When we were in this part of the galaxy last time, the world was a completely different place. And 2 galactic years ago, the Earth was filled with strange amphibious life and giant forests of ferns and moss. We have traveled so far. The stars we see tonight were not always our neighbors. As we orbit, we drift past other stars. We move through different arms. The constellations change over millions of years. The night sky is a fluid canvas. The stars we see today weren't always nearby, and they won't always remain. Everything is passing. Everything is flowing. Even as we sleep, the Earth turns, the Moon circles, and the entire solar system sweeps forward through a galaxy in motion, carrying us into new regions of the dark. And just as we move, the galaxy itself changes. The galaxy is still growing. We tend to think of the Milky Way as a finished object, like a painting dried on a canvas, or a building completed and standing tall. But it is not finished. Even now, in the silence of space, it continues to gather new material. It is feeding. It grows not like a living thing with hunger, but like a gravitational structure deepening over time. There are clouds of pristine gas drifting in from the intergalactic medium. These clouds fall towards the disk, pulled by gravity. They arrive, slowly replenishing the galaxy, providing fresh fuel for new stars. There are streams of dark matter that feed its halo, adding mass, adding weight to the invisible scaffolding that holds us together. Some of this growth happens quietly. Through the gentle infilling of these clouds, a soft rain of hydrogen falling onto the galactic plane. Other times, it comes with disruption. As we mentioned before, satellite galaxies are torn apart. Their stars are scattered across the sky. It is a process of assimilation, a process of weaving separate threads into a single grand tapestry. The galaxy you live in today is not the same one the dinosaurs saw. It is slightly heavier, slightly larger, its shape subtly altered by the passage of time. And the galaxy that your distant descendants may know billions of years from now could be larger still, stitched together from the ruins of 1,000 smaller worlds. It is a masterpiece that is never quite done, always painting itself anew, always turning, always growing in the quiet dark. We often imagine that we know what our galaxy looks like. We see illustrations, paintings, computer simulations. We see a beautiful multi-armed spiral, a pinwheel of blue and white light. But the truth is, we do not actually know how many arms the Milky Way has. It seems like something we should know. A basic fact, like the number of continents on Earth, or the number of planets around the Sun. How many arms spiral from the center of our own galaxy. But we must remember our perspective. We are inside the structure. Imagine standing in the middle of a dense forest on a foggy day. You can see the trees immediately around you. You can see shadows further out. But you cannot see the shape of the forest. You cannot tell if it is round or square or shaped like a star. That is our predicament in the Milky Way. From our position deep inside the disk, about halfway out from the center, it is hard to see the whole structure. There are vast, thick clouds of interstellar dust. They act like curtains. They block the light from distant regions. They obscure the far side of the galaxy. Stars blur into one another. Distances become difficult to measure. For decades, astronomers believed there were 4 major spiral arms: the Norma arm, the Scutum Centaurus arm, the Sagittarius arm, and the Perseus arm. Maps were drawn, models were made. But more recent observations using infrared telescopes that can peer through the dust suggest something different, something more complex. Maybe there are fewer arms. Maybe only 2 main arms that branch out into smaller spurs and fragments. Or perhaps the arms twist and split in ways more intricate than we expected. Some arms fade into nothingness. Others wrap around unexpectedly, connecting where they shouldn't connect. The Milky Way may not be a neat symmetrical pinwheel at all. It may be a living, layered swirl of stars. Messy, beautiful, and shaped by forces we still do not fully understand. It is a mystery we live within, a puzzle we are trying to solve from the inside out. And within this swirl, most stars are obedient. They follow the flow. They drift calmly through the galaxy, orbiting the center in the same direction at roughly the same speeds, like cars on a highway or water in a whirlpool. But there are exceptions. There are rebels in the dark. Rogue stars. These are stars that have been flung from the core. A rare few that are moving at astonishing speeds, fast enough to escape the Milky Way entirely. Astronomers call them hypervelocity stars. The name itself sounds fast, but the reality is even more intense. These stars are likely the remnants of binary systems. 2 stars orbiting each other, living together. But then they drifted too close to the center. Too close to the supermassive black hole that lies at the heart of the galaxy. Gravity is a cruel master in the core. The black hole captures one star. It pulls it in. It consumes it or traps it in a tight, doomed orbit. But the other star, the partner, it is not captured. Instead, it is slingshotted. Using the immense energy of the encounter, it is hurled outward, thrown into the dark at over 1,000,000 kilometers per hour. Imagine the force. Imagine the speed. These rogue stars travel alone. They pierce through the disk. They race through the halo, far from the warmth of their birthplace, far from the crowded, bright clusters of the core. They are like glowing comets made of plasma, with no return ticket. They will eventually leave the Milky Way altogether. They will cross the invisible border of our galaxy and enter the profound emptiness of intergalactic space. There, they will drift forever, solitary lights in the endless, starless void. They remind us that even in a galaxy bound by gravity, there are moments of violent release, quiet expulsions that send stars flying into the eternal night. Let us turn our gaze outward again, away from the rogue stars fleeing into the void and toward a shape looming in the distance. if you were to stand under a perfectly dark sky, far from the glow of cities, and look toward the constellation of Andromeda, you might see it. A faint, fuzzy patch of light. A smear no wider than the full moon. It looks small. It looks harmless, like a wisp of cloud that refuses to move with the wind. But this is the Andromeda Galaxy, Messier 31, a colossal island universe containing perhaps 1 trillion stars. It is a spiral much like our own, but larger, more massive, and it is lying over 2.5 million light-years away. That distance is a chasm so deep that the light you see tonight left Andromeda before human beings existed. It traveled through the empty, cold silence between galaxies, while ice ages came and went, while species rose and fell. And yet, despite this distance, it is moving, steadily, relentlessly, toward us. The Milky Way and Andromeda are falling together, drawn by the invisible, unbreakable tether of mutual gravity. We are on a collision course, but do not worry. This is not a disaster for today, or tomorrow, or even for the next billion years. This is a slow-motion event, a convergence taking place on a timescale that geology itself would find slow. In about 4.5 billion years, the view from Earth will be spectacular. Imagine the night sky of that distant future. The Milky Way will still arch overhead, but Andromeda will have grown. It will no longer be a faint smudge. It will dominate the heavens, a second spiral tilted in the sky, filling the dark with its glowing core and sweeping dusty arms. It will look like a storm of light approaching from the horizon. And then the merger will begin. As the two galaxies pass through each other, the sky will be distorted. Gravity will pull long streamers of stars out of their orbits. Tidal tails, vast arcs of blue and white, will be flung across the firmament. The supermassive black holes at the centers of both galaxies will spiral inward, dancing closer and closer until they merge. Eventually, the spiral shapes will be lost. The two galaxies will settle, the chaos will quiet down, and a new galaxy will form, a giant elliptical galaxy, vast, round and quiet. Some astronomers call this future home Milkomeda. It will be a slow, elegant dance. The future of our home written across the stars long before it ever comes to pass. But even now, within our own galaxy, not everyone is following the rules. If we look closely at the motions of the stars, we find anomalies. Most stars in the Milky Way orbit the center in a flat plane. They move together. A great, glittering carousel turning in unison. But some stars orbit backward. They are moving in retrograde. Imagine a highway filled with millions of cars, all driving east. And then, scattered among them, are a few solitary drivers heading west, moving against the flow, swimming upstream against the current of light. These stars are mostly found in the outer halo, far from the order of the main disk. Why do they move like this? Why do they defy the rotation of the rest of the galaxy? The answer is likely found in their origins. These stars are strangers. They were not born here. They likely arrived from elsewhere. Born in dwarf galaxies that were captured and absorbed billions of years ago. When a small galaxy falls into the Milky Way, it comes in at a random angle. It might fall in sideways, or vertically, or backward against the spin. As the dwarf galaxy is torn apart, its stars keep that momentum. They continue to travel along the paths they were on when they arrived. Their reversed motion is a quiet signature, a fingerprint of their foreign origin. It is as if the galaxy carries old memories in its motion, stories of ancient mergers and cosmic encounters, preserved not in books or stone, but in the slow, patient turning of stars against the stream. This brings us to a deeper truth. The Milky Way is a cannibal. It may have eaten dozens of dwarf galaxies. Throughout its life, the Milky Way has not grown alone. It has consumed small galaxies. Faint, low-mass companions have drifted too close. They were caught in the gravity well, trapped like leaves swirling down a drain. Slowly, over hundreds of millions of years, they were dismantled, their structures unraveled, their gas siphoned off to feed our own star formation, their stars scattered to become part of our halo or our disk. Astronomers have identified several of these mergers. They do this by analyzing stellar motion and composition. One especially large event is known as the Gaia-Enceladus merger. It happened long ago, perhaps 10 billion years ago. A substantial galaxy smashed into the young Milky Way. It added billions of stars to our halo. It heated up the galactic disk. It may have reshaped the entire structure of the early galaxy. The Milky Way we see today is not a pristine, untouched spiral. It is a composite, a mosaic, built from quiet collisions, stitched together from the remains of many smaller worlds. Everywhere we look, we see the ghosts of galaxies past. How do we know this? How can we tell which stars are natives and which are immigrants? The answer lies in chemistry. The chemical makeup of stars reveals their origin. Every star carries a unique chemical fingerprint, a pattern of elements imprinted on it at the moment of its birth. When a star forms, it collapses from a cloud of gas. That cloud contains a specific mix of elements: hydrogen, helium, trace amounts of iron, calcium, oxygen, magnesium. When the star ignites, that mixture is locked into its atmosphere. It stays there, burning for billions of years. By studying these signatures using the science of spectroscopy, splitting the light into a rainbow of colors, and looking for dark lines, astronomers can trace a star's history. Some stars are rich in heavy elements. Like our Sun, this suggests they formed in dense, metal-rich regions, likely in the main disk of a large galaxy, where many generations of stars had lived and died before, enriching the gas. Other stars are poor in metals, nearly pure. These likely formed in the early universe or in small, dwarf galaxies where star formation was slow and the gas was never enriched. These differences allow scientists to group stars into families. We can find clusters of stars scattered across the sky that are thousands of light years apart, but share the exact same chemical fingerprint. Like siblings, separated at birth, we can uncover ancient mergers. We can reconstruct the hidden story of the Milky Way's formation. In this way, chemistry becomes a kind of time machine, letting us read a star's past like a line of ancient poetry written in light. And sometimes the evidence is even more direct. The sky is full of stellar streams. These are ribbons from shredded galaxies. Across the sky, above and below the galactic plane, thin streams of stars stretch in arcs and curves. They are barely visible, too faint to be seen without sensitive instruments. But when mapped with precision, they are unmistakable. They look like scratches across the darkness. These are the remnants of the smaller galaxies that wandered too close. As they orbited, as they were pulled apart, their stars were smeared across space, like paint on a spinning canvas. Tidal forces dragged them out, forming long, delicate trails that trace their former paths. Some of these streams wrap around the galaxy like ghostly halos. Others dive in toward the core. Some are thin and sharp, others are broad and diffuse. There is the Orphan Stream, the Helmi Stream, the Sagittarius Stream, each one named for what it was or where it was found. These streams are evidence of past collisions, quiet mergers that built the Milky Way over eons. The galaxy, like a great, ancient tree, carries the rings of its past. Not in wood, but in every thread of light that circles it. But the shape of the galaxy is not perfect. The Milky Way is warped. We often see diagrams showing the galaxy as a flat disk, like a dinner plate or a frisbee. But reality is more organic, more fluid. Our galaxy doesn't lie flat, its disk bends. It curves upward on one side and downward on the other. Imagine a vinyl record that has been left in the sun too long. It warps, it curls. This is the shape of our home. It forms a graceful wave across the stars. This subtle warp was invisible to us for a long time. Because we are inside it, it is hard to detect the curve. But radio telescopes mapping the hydrogen gas that stretches far beyond the starlight revealed the truth. The gas flares out, and it bends. Why? Why is our galaxy bent? Astronomers believe the distortion may be caused by satellite galaxies. Perhaps the Large Magellanic Cloud, orbiting nearby, is tugging gently on the Milky Way's edges, like someone pulling on the corner of a bedsheet. Or perhaps it is caused by clumps of dark matter bending the structure from below. Or maybe it is the lingering vibration of a past collision, a ripple that has not yet settled down. Like ripples in a great spinning sheet, the warp reveals that even galaxies are never fully still. They are flexible, they bend, they flex, and they change form in response to invisible forces. From a distance, if we could fly out millions of light years away and look back, the Milky Way might look like it is dancing, slowly, turning and swaying through space. And yet, from where we stand, on the surface of the Earth, we see so little. You can only see about 0.0003% of the Milky Way with the naked eye. Think about that number. Think about how small that fraction is. Under a clear, dark sky, far from cities, far from streetlights, where the velvet darkness is total, you might see a few thousand stars, perhaps 2,000, maybe 3. To the human eye, that seems like an infinity, an ocean of light, diamonds scattered on black velvet. It feels overwhelming. It feels like we are seeing the whole universe, but it is barely a droplet. It is barely a speck of dust in the grand scheme. The Milky Way contains over 100 billion stars. Some estimates say 200 billion, others up to 400 billion. Most of them are hidden from view. Some lie behind thick curtains of dust. The same dust that births new stars blocks the light of the old ones. Others are simply too faint. Red dwarfs, small, cool stars that make up the vast majority of the population. They are everywhere. But they are so dim that our eyes cannot detect them, even if they are nearby. And others are simply too far away, across the galactic core. On the other side of the spiral, the pale streak of the Milky Way that crosses the sky on moonless nights. is just the innermost whisper of the whole. It is the combined glow of millions of distant stars blurring together. We live surrounded by a colossal river of starlight, and yet almost all of it remains invisible to us. Too vast to grasp from within. We are standing on a small island, peering out into a boundless sea, seeing only the waves that break upon our shore. Let us drift now into the mechanics of this sea, into the way it moves, because stars orbit the galaxy at different speeds. In our solar system, we have a simple rule. Kepler's laws. Planets closer to the Sun orbit fast. Mercury zips around in just 88 days. Planets farther away orbit slowly. Neptune takes 165 years. It is a predictable falling off of speed. But the galaxy does not work quite like that. Unlike planets which follow neat tracks around a single dominant star, stars in the Milky Way move with more freedom. They are influenced by the gravity of everything around them, the gas, the dust, the other stars, and the dark matter. Some stars race ahead in the inner regions. Others drift slowly along the outskirts. But this difference in speed is why spiral arms form. The arms are not solid structures. They are not rigid spokes on a wheel. If they were rigid, the galaxy would wind itself up tightly and lose its shape within a few rotations. Instead, the arms are patterns. They are density waves. Imagine a traffic jam on a highway. The cars slow down as they enter the jam. They bunch up. It gets dense. Then they speed up and leave the jam behind. The traffic jam itself moves down the highway, but the cars move through it. This is a spiral arm. It is a cosmic traffic jam. Stars and gas clouds drift into the arm. They slow down. They bunch up. Gravity increases. Gas is compressed. And this compression triggers new stars to form. That is why the arms are blue and bright. They are lit up by the fires of newborn suns. Massive, hot, blue stars that live fast and die young. They light up the arm like a neon sign. But as the wave passes, or as the stars move on, the arm shifts. Our own sun is part of this swirl. We are currently drifting in a quiet spur. But we move in and out of these patterns across time. The galaxy is not a clock. It is a current, and we are drifting in it. But there is a mystery in this movement. The galaxy holds together because of something we cannot see. By all logic, by all the laws of classical physics, the Milky Way should not exist. At least, not in its current form, based on what we can measure, based on the stars we can count, the dust we can weigh, the gas we can map. The outer edges of the galaxy are spinning too fast. Centrifugal force should be overwhelming. The stars on the rim should be flung into space. Scattered like leaves in a storm, the galaxy should dissolve. It should fly apart into a diffuse, unstructured mist, and yet it remains. It holds its shape. The stars stay in their orbits. The spiral keeps its form. Why? What is holding it so tightly? The answer is dark matter. This mysterious substance is the ghost in the machine. It does not shine. It does not reflect light. It does not emit radio waves or X-rays. It passes through ordinary matter without touching it. But it exerts gravity, and there is so much of it. It outweighs all the visible matter in the galaxy many times over. Imagine looking at a Christmas tree in the dark. You see the lights, the colored bulbs floating in the blackness, but you cannot see the branches. You cannot see the trunk. You cannot see the tree itself. The stars are the lights. Dark matter is the tree. It is the invisible scaffolding that holds everything in place. We are embedded in a vast cloud of this matter, a halo that extends far beyond the visible spiral. We don't know what dark matter is. Is it a particle? Is it a flaw in our understanding of gravity? We don't know. But we know that without it, the Milky Way would fly apart. It is the silent, heavy hand that keeps us home. Now, let us travel inward, past the spiral arms, past the dust lanes, toward the very heart of the galaxy. There is a supermassive black hole at the core. At the very center of the Milky Way lies an object of terrifying power and absolute silence. It is a singular point of gravity. It is called Sagittarius A, pronounced Sagittarius A star. It is a name that sounds technical, but represents something profound. It is more than 4 million times the mass of our Sun. Take the Sun, that colossal ball of fire, and multiply it by 4 million. Then crush all of that mass down, smaller and smaller, until it occupies a space smaller than the orbit of Mercury. That is the black hole, a tear in the fabric of space-time, a bottomless well where gravity becomes infinite. We cannot see it directly. Black holes trap light. Nothing that crosses the event horizon can ever return. It is a shadow in the dark. But we know it is there. We have watched. For decades, astronomers, using powerful infrared telescopes, have tracked the stars at the galactic center, and what they saw was astonishing. These stars, called the S-stars, are whipping around an invisible point. They are moving at tremendous speeds, tracing invisible loops through the void, turning sharply around nothing. Only an object with the mass of 4 million suns could force a star to move like that. Sometimes gas and dust fall inward. They spiral closer and closer to the edge. As they fall, they heat up. Friction and gravity tear them apart. They flare with X-rays. Brief, bright sparks before they vanish forever into the shadow. For now, Sagittarius A sleeps. It is relatively quiet. Compared to other galaxies, where the black holes are voracious eaters, ours is on a diet. It is starving, dormant. But long ago, it may have burned like a quasar. It may have lit up the entire galaxy from within. It is the silent conductor of the Milky Way's heart, pulling stars into a slow, relentless dance, anchoring the center of our world. And surrounding this black hole is a strange structure. The Milky Way has a peanut-shaped bulge. When we imagine the center of a galaxy, we usually think of a smooth, round ball of stars, like the yolk of an egg, glowing warmly in the middle. But when astronomers mapped the center of the Milky Way, using infrared light to peer through the dust, they discovered something unexpected. The central bulge is not round. It is peanut-shaped, or perhaps like an X, or a twisting hourglass made of stars. Seen from the side, it swells in the middle and narrows at the ends. This strange geometry is not an accident. It is a structure built by gravity. It likely formed from the galaxy's central bar, a dense stripe of stars that rotates slowly. Over billions of years, this bar buckled. It puffed upward and downward, like dough rising in an oven, or waves crashing together. These inner structures are sculpted by billions of years of motion, the accumulated rhythm of stellar orbits stacking on top of one another. We live in a spiral galaxy, but its heart is full of complexity. Not flat, not clean, but intricate, layered, and alive with geometry we are only just beginning to understand. Let us drift back out from the core, back to the arms, where creation is happening. Stellar nurseries shape the spiral arms. The Milky Way's arms are not simply made of stars. They are woven from the birthplaces of stars. Giant clouds of molecular hydrogen, dust, and simple molecules drift through the galaxy. They are cold, dark, silent. But when these clouds pass through the density waves of the spiral arms, something happens. They are squeezed, compressed, shocked. The pressure rises, gravity takes hold, and within the darkness, points of light begin to ignite. These regions are called stellar nurseries. Like the Orion Nebula or the Lagoon Nebula, they are chaotic, glowing, and full of motion. Ultraviolet light from the massive, newborn stars blasts outward. It carves caves in the clouds. It lights up the gas, painting the arms with radiant blues and pinks and silvers. These bursts of creation trace out the spiral shape, illuminating the curves of the galaxy with quiet fire. Every star that you see, even our own sun, was born from one of these cloudy cradles long ago. We are all children of the dust and the arms. Let us drift higher now, above the plain, above the dust lanes, above the bright, blue arms of the spiral. If we could float far above the Milky Way, looking down, we would see the disk, glowing like a city at night. But surrounding it, enveloping it, is something else. The Milky Way is surrounded by a vast halo. Beyond the flat, spiral disk lies a region far more diffuse, far more ghostly. A spherical halo of immense proportions. It surrounds the entire galaxy like a sphere of glass, encasing a flat jewel. But this sphere is not made of glass. It contains ancient stars, globular clusters, and enormous amounts of dark matter. Though it is nearly invisible to the naked eye, this halo may hold the majority of the Milky Way's mass. Its stars are spread thin. The distance between them is vast, a lonely, silent expanse. They orbit in long, slow arcs, plunging through the disk and soaring back out into the emptiness. They rarely touch the disk. They rarely interact with the crowded, busy regions where we live. The halo also preserves the remnants of ancient galactic mergers, streams and shells of stars torn from smaller galaxies and left behind, like cosmic fossils or footprints in the snow. It is the galaxy's outer memory, quiet, dim, but still in motion, still shaping what the Milky Way becomes. It is the container in which the galaxy lives. And within this halo, floating like lanterns, are jewels. It contains over 150 globular clusters. These are among the oldest objects in the galaxy. Perhaps the oldest objects in the universe. Globular clusters are compact spheres, balls of stars, tightly bound by their own gravity. Imagine hundreds of thousands of stars, sometimes a million stars, packed into a space only a few light years across. In the core of a cluster, the stars are so close that night would never fall. The sky would be a blazing roof of a million suns. They orbit the galactic center in the halo, like moths circling a distant flame, or satellites around a planet. These clusters are incredibly stable. They have survived for aeons. Some are more than 12 billion years old. Many contain stars that predate the formation of the Milky Way itself. Their stars are metal poor, ancient, red and gold. They formed before the universe had time to create many of the heavier elements. They serve as time capsules, holding clues to how the galaxy formed, what it consumed, and what conditions were like. In the early cosmos, these quiet, golden spheres drift patiently above and below the galactic plane, glowing in the dark, silent sentinels, watching the spiral turn. But let us return to the idea of growth, because the galaxy is not dead. The galaxy is still growing. Although the Milky Way is ancient, it isn't finished. Even now, in the deep silence, it continues to gather material. It is a slow accumulation. Gas from the intergalactic medium drifts in, cooling, condensing, falling onto the disk. Stars from captured dwarf galaxies are added to the population. Streams of dark matter thicken the halo. It grows not like a living thing that breathes and eats rapidly, but like a gravitational structure, deepening over time. Like a mountain growing from tectonic pressure, or a stalactite growing from dripping water, slowly, invisible to the human eye, but relentless. Some of this growth happens quietly, through infilling clouds. Other times it comes with disruption, as satellite galaxies are torn apart. The galaxy you live in today is larger than the one the dinosaurs saw, and the one your distant descendants may know could be larger still. Stitched from the ruins of 1,000 smaller worlds. And while the galaxy gathers, it also loses. Rogue stars are flung from the core. We spoke of these earlier, the hypervelocity stars. But let us consider them again in their loneliness. Most stars drift calmly. They are part of the herd. But a rare few are flung outward at astonishing speeds, fast enough to escape the Milky Way entirely. Some are the remnants of binary systems disrupted by the supermassive black hole. One star falls in, vanishes. The other is slingshotted outward, hurled into the dark at over 1 million kilometers per hour. These rogue stars travel alone, far from the galactic plane, like glowing comets with no return. They remind us that even in a galaxy bound by gravity, there are moments of violent release. Quiet expulsions that send stars flying into the intergalactic night. They are the exiles, carrying the light of the Milky Way into the profound darkness between the islands of the universe. But what of the stars that remain? What of the creation of new light? Star formation is slowing down. Long ago, in the early days, the Milky Way was more active. It was bursting with fresh stars, born from dense, collapsing clouds. The galaxy was a firework display of blue and white, but in recent epochs the pace has slowed. The galaxy is aging. There is still gas available, but much of it is spread thin, or it is heated by supernova explosions, making it too hot to collapse, or it is locked in forms that resist gravity. The galaxy is not done making stars. It still creates them. In the Orion Nebula, in the Eagle Nebula. But it is settling, like a fire that has burned down to glowing coals. Astronomers estimate that star formation peaked billions of years ago and has been declining ever since. This does not mean the end is near. Far from it. Only that we live in a quieter chapter, a mature spiral, glowing gently in its middle age, still forming stars, but no longer in a hurry. It is a time of stability, of steady, calm light. And in this calm we find ancient relics. Some stars, formed before the Milky Way, had a disk, the disk. That broad, flat spiral we think of as the Milky Way. It formed gradually, over time, as the gas settled, as gravity flattened the cloud. But some of the stars in our galaxy are older than the disk itself. These ancient stars reside mostly in the halo, or in the thick disk, a puffy layer of old stars. They formed when the galaxy was still assembling, when it was just a loose cloud of stars, gas, and dark matter, slowly collapsing inward. By studying their composition and their motion, astronomers can peer back into the era before structure, before spirals, before the familiar shape emerged from the chaos. These stars are the elders of the galaxy, silent witnesses to its birth and the long, slow shaping of what we now call home. Let us consider time again. Deep time. Galactic time. A galactic year is about 225 to 250 million Earth years. As the Sun orbits the center of the Milky Way, it completes one full revolution every few 100 million years. This is a vast cycle, a clock that ticks in aeons. In the time it takes for the Sun to circle the galaxy once continents drift across the face of the Earth, mountains rise and are worn down to hills, oceans open and close, species rise and fall. Entire epochs of geological history unfold in a single galactic season. It is thought that we are currently about halfway through one such orbit. The last time the solar system was in this part of its path, the supercontinent Pangaea had just begun to break apart. Dinosaurs had not yet emerged. The world was on the brink of a new era. A galactic year is the slow heartbeat of cosmic time, a rhythm too slow for us to feel, but one that governs the long life of our system. The Sun has completed fewer than 25 galactic orbits. In all of its 4.6 billion years of existence, the Sun has only circled the Milky Way around 20 times, perhaps 22. That is fewer than you might expect. We think of the Sun as eternal, ancient. But in the context of the galaxy, it is a traveler who has only made a few trips around the world. Considering its incredible speed, nearly 830,000 kilometers per hour, it is humbling to realize how large the galaxy is. We often think of the stars as ancient and unmoving, but our solar system is still young on a galactic scale, a newcomer in a city of older, more traveled suns. We are part of the galaxy's motion, but still early in its long, winding story. But there is a puzzle in this motion. The Milky Way's rotation defies Newton's predictions. Sir Isaac Newton, the father of gravity, his laws explain the orbits of the planets perfectly. Mercury moves fast. Pluto moves slow. The farther out you go, the weaker gravity gets and the slower you orbit. It makes sense. It is logical. But in the Milky Way, it doesn't work. Stars far from the galactic center should orbit more slowly, just as outer planets move more leisurely around the Sun, but they don't. In the Milky Way, stars in the outer regions orbit almost as quickly as those near the center. The rotation curve is flat. It defies classical expectations. It breaks the rules of the visible universe. The reason, once again, it is the ghost. Dark matter, an invisible, unknown form of mass that surrounds the galaxy in a vast halo. It adds gravity, it adds mass, where we see nothing. Without dark matter, the galaxy would not hold together. The outer stars would fly off with it. The math works. The Milky Way turns like a solid wheel, not because we understand it fully, but because something unseen is holding it in place, pinning the stars to the dark. And floating within this dark matter are clouds. The galaxy has enormous molecular clouds. Scattered throughout the Milky Way are vast, dark reservoirs of cold gas, the raw material of stars. These molecular clouds, composed mostly of hydrogen molecules and traces of dust, can span hundreds of light years across. They are the giants of the interstellar medium. Within their cold, dense interiors, gravity begins to gather material, forming clumps, knots in the gas, that collapse into new stars and planets. Some of these clouds are so large and so cold that they absorb visible light entirely. They appear as black patches against the starry sky, like holes in the heavens, or ink spilled on a photograph. They are the galaxy's wombs, quiet, hidden places where the future begins in silence, tucked within curtains of shadow and gas. But creation is often violent. Supernovae stir the galaxy like storms. When massive stars reach the end of their lives, they do not fade away quietly. They explode in cataclysmic events called supernovae. Events so powerful they can outshine entire galaxies for a brief moment. But these explosions don't just end lives, they create. Shock waves from supernovae ripple through the interstellar medium, like waves from a stone thrown into a pond. These waves compress nearby clouds. They squeeze the gas, triggering new waves of star formation, death leading to birth. They also enrich the surrounding space with heavy elements, like iron and gold and calcium, forged in the heart of the dying star. In this way, supernovae act like storms within the galactic ecosystem, stirring, fertilizing, and reshaping everything around them. They are the galaxy's moments of chaos, destructive, radiant, and necessary for the cycle of life. But often, we cannot see this cycle. Dust hides vast regions of star formation. The Milky Way is full of light we cannot see. Interstellar dust, made of microscopic grains of carbon, silicate, and ice, weaves through the galaxy. In clouds and tendrils, it acts like smoke. Invisible light, it obscures vast regions of space, blotting out stars and entire nebulae. The Great Rift, a dark band running through the Milky Way, is simply dust, blocking our view. But behind this veil, star formation continues. Infrared telescopes can peer through the dust, revealing glittering nurseries filled with newborn suns. What looks like darkness is often a cradle. The dust, though it hides, is part of the process. It absorbs energy, helping gas cool and shielding delicate stages of stellar birth. What seems like emptiness is often the beginning of something bright, and not all clouds are active. There are starless gas clouds drifting through the galaxy. Not every cloud of gas becomes a star. Across the Milky Way, astronomers have found massive, cold clouds that seem destined for collapse, yet remain dark and dormant. Some are too diffuse, too spread out. Others may be stabilized by magnetic fields, holding them up against gravity, or by internal turbulence, mixing the gas, preventing it from settling. These starless clouds float through the galaxy like silent possibilities, rich in molecular hydrogen, but untouched by fusion. They may one day ignite, or they may drift until torn apart by external forces. Their gas recycled into other regions. In these clouds, the galaxy holds its breath, waiting perhaps for the right nudge to spark something new. This leads us to the great cycle. The Milky Way recycles matter across generations. Stars are not permanent. They live, they burn, and they die. And in dying, they return their material to the galaxy. It is a cosmic ecology. Supernova spread heavy elements. Red giants shed their outer layers gently into space. Planetary nebulae drift outward, like glowing rings of smoke. This enriched material joins the interstellar medium, where it cools, condenses, and eventually forms new stars, new planets, and even life. Every atom in your body, the carbon in your cells, the iron in your blood, the calcium in your bones, has passed through this cycle, born in a star, scattered into space, gathered into new form. The Milky Way is not a static stage, but a great engine of renewal. It breathes in time with its stars making, unmaking, and beginning again. Let us look again at the ancient ones. Metal, poor stars hold clues to the early universe. In astronomy, metals represent age. The earliest stars in the universe had almost none of these metals, because they formed before earlier generations of stars had a chance to forge and scatter them. Today, astronomers seek out metal-poor stars in the halo of the Milky Way. These stars, faint and ancient, preserve the chemical conditions of a time long gone. By analyzing their composition, we peer into the primordial past, into the period just after the Big Bang, before galaxies had matured, before the galaxy itself had taken full shape. They are fossils made of light, allowing us to read the first chapter of the story. But stars do not always stay put. Some stars wander far from where they were born. A star's birthplace doesn't always define its destiny. Over time, many stars drift away from their natal clouds, pushed by gravitational interactions, orbital resonance, or the slow pull of spiral arms. Some stars are ejected at high speeds, flung across the disk, or into the halo. Others migrate gradually, radial migration, shifting their orbits inward or outward as they spiral through the galaxy. Even our Sun is not where it began. It has likely moved thousands of light years from its birthplace. Tracing the paths of stars reveals a Milky Way that is anything but static, a galaxy alive with movement, exchange, and quiet dislocation. Home for a star may only be temporary. Let us drift now to the idea of home. Not just our planet, but the neighborhood in which we live. Is there a specific place in the galaxy that is best for life? Astronomers believe so. The galaxy's habitable zone may span tens of thousands of light years, just as Earth orbits in a Goldilocks zone around the Sun. Not too hot, where water would boil. Not too cold, where water would freeze. But just right. The Milky Way may have its own galactic habitable zone. This region is thought to lie between the dangerous inner core and the sparse outer edge. In the core, star density is high. Supernovae explode frequently. Radiation levels are intense. Black holes prowl. It is a crowded, violent city. A difficult place for biology to take hold and survive for billions of years. On the other hand, the outer edges are too empty. The stars there are metal poor. There isn't enough iron or silicon or carbon to build rocky planets like Earth. Planets there might be gas giants or nothing at all. But somewhere in between lies a wide band, a ring where conditions are stable, where star density is moderate, and elements like carbon, oxygen, and iron are abundant. Earth lies within this zone, one quiet orbit in a vast swirl, where life might not be alone in finding a foothold. It is a sweet spot in the spiral. But even this sweet spot is not static. The spiral arms are not fixed structures. The Milky Way's spiral arms might seem like permanent features. Grand, sweeping lines carved into the galaxy's disk. like the grooves on a record. But they are not made of fixed stars. They are patterns. Density waves, ripples moving slowly through the disk, compressing gas, triggering new stars. Stars drift into these arms. They shine for a while, and then they drift out again. The spiral structure moves at a different speed than the stars themselves, like a traffic jam, moving through a highway. From afar, it looks like form. It looks like order. From within, it is a pattern of shifting motion, held together by gravity and time, never still, always flowing. And beneath the flow, there is energy. The Milky Way hums with cosmic radiation, beyond visible light, beyond what our eyes can see. The galaxy glows with mysterious forms of energy, cosmic rays, high-energy particles, born in supernova and distant galaxies, stream through space. They pass through your body every second. X-rays and gamma rays shimmer from dying stars and black holes. Radio waves drift from gas clouds, from pulsars, and from the cold breath of hydrogen. These invisible hums reveal what light cannot. The violence, the magnetism, the ancient fires still flickering within the galaxy's bones. When you look into the night sky, you are only seeing a narrow band of the Milky Way's true spectrum. Beneath the stars, the galaxy hums softly, in many colors, in many frequencies, a hidden symphony in the dark. And speaking of hidden things, there are giants looming above us. There is a giant gamma ray bubble above and below the core, stretching tens of thousands of light years above and below. The galactic center are two vast ghostly lobes of high-energy light. They are called the Fermi bubbles, discovered only recently by space telescopes. They glow in gamma rays, extending like twin balloons from the Milky Way's heart, or like the wings of a giant, invisible insect. No one is entirely sure what caused them. They may be the remnants of a long-ago outburst from the central black hole, a sudden belch of energy millions of years ago, or perhaps the mark of fierce star formation that once flared through the core. Either way, these enormous structures drift silently over the galaxy. Invisible to human eyes, they are reminders that the Milky Way has a past we cannot fully see. Echoes of violence, wrapped in radiance far above the stars we know. Let us return to our location, to our quiet street in the galactic city. We live in a minor spur between major arms. Our solar system doesn't lie in one of the Milky Way's grand spiral arms. We are not in the Perseus arm. We are not in the Sagittarius arm. Instead, we occupy a small structure, a bridge called the Orion Spur, a relatively quiet lane of stars, nestled between the larger arms. It is not especially dense, nor especially active, but that may be why we are here. In the calm between galactic highways, massive supernovae are rarer. Radiation storms are less frequent. Traffic is light. This quiet corner may have given life on Earth the time it needed to emerge, to evolve, to survive. From the outskirts, the galaxy seems dramatic, radiant, busy. But in this quiet spur, we found just enough peace for complexity to unfold. We are hiding in the safe harbor of the spiral. But the center is structured differently. The Milky Way has a bar-shaped center. When astronomers look toward the galactic core in infrared light, they see not a perfect circle, but a thick, elongated bar of stars crossing the middle, like the hub of a great wheel or a glowing bridge. This bar rotates slowly, like a propeller, and its gravitational pull shapes the inner spiral arms. Bars like this are common in spiral galaxies. They form when stars in the disk begin to drift inward and pile up along a central axis. Over time, the bar becomes a stable structure, starring gas, triggering new stars and feeding material toward the black hole at the center. It is not just a shape, but a dynamic engine, sculpting the galaxy's heart from within. And looking even further out, we realize we are not alone. It is part of a larger structure called the local group. The Milky Way doesn't exist in isolation. It belongs to a collection, a neighborhood of more than 50 galaxies, known as the local group, a small cluster drifting together through space. The two largest members are the Milky Way and Andromeda, the two giants, each with its own family of satellite galaxies. Scattered around them are smaller dwarfs, faint ellipticals, and star-poor galaxies made almost entirely of dark matter. The local group spans more than 10 million light-years, and it is bound together not by proximity alone, but by gravity. We are part of the family, quiet, widely spaced, but still linked by the invisible threads of shared motion and mutual pull. And this family sticks together. Galaxies in the local group are gravitationally bound, despite their vast separations. Despite the expansion of the universe, which is pulling most galaxies apart, the galaxies of the local group are not drifting away. In fact, many are moving slowly toward one another. Gravity holds them in a kind of slow motion bullet, curving their paths across millions of years. Some of the smallest galaxies orbit the Milky Way like moons, looping and falling, dissolving into streams. Others drift independently, but remain tethered, caught in a web of shared motion. Over time, this group may condense. Galaxies may merge, fade, or be absorbed. It is not a static arrangement, but a gentle gathering of cosmic islands, a family drawn closer by time, inertia, and the long reach of gravity. Now let us look at the texture of our home. The galaxy's disk has a thick and thin component. The Milky Way's disk looks flat from a distance, like a CD or a pancake. But up close it is layered. The thin disk is where we live. It is a wide, dense plain, filled with young stars, open clusters, and star-forming gas. It is the bright, active layer. But above and below it lies the thick disk, older, puffier, more diffuse. Stars in the thick disk tend to be older, with fewer heavy elements. They move in orbits that are more tilted and elliptical, suggesting they formed under different conditions or were stirred up by early galactic collisions. The galaxy's disk is not uniform, it's textured, layered, shaped by time, like sediment settled on the floor of a cosmic ocean, or the rings of a tree showing seasons of growth. And threading through this disk is a force field. The galaxy's magnetic field threads through the disk. Though invisible to the eye, the Milky Way is laced with a vast magnetic field, stretching across the disk, rising into the halo, and weaving through the interstellar medium. This field is weak by earthly standards, thousands of times weaker than the magnet on your refrigerator. But over galactic distances, it is powerful. It shapes how cosmic rays travel. Bending their paths, it influences how gas clouds collapse, supporting them against gravity, and how matter flows through space. It aligns with spiral arms. It forms arcs above the plane, and twists into loops that defy simple explanation. Studying it requires radio telescopes, and careful analysis of polarized light. But its presence is unmistakable. The Milky Way does not just glow with light. It breathes with magnetism, a subtle pulse running through its bones. And between the bones, there is structure. The interstellar medium is full of invisible structures. Between the stars lies more than emptiness. The interstellar medium, that thin blend of gas, dust, and plasma, weaves its way through the Milky Way like a fog. To the naked eye, it is mostly invisible. But when viewed with radio and infrared telescopes, it reveals a stunning complexity. It forms filaments, long, thin threads of gas, bubbles, blown by stellar winds, shock waves, rippling through the void, and cold, dense clouds where stars are born. Supernovae carve vast cavities in it. Stellar winds sculpt it into shapes that ripple across light years. The space between stars is not a void, but a shifting web of matter and magnetism, the quiet fabric from which galaxies evolve, and life eventually begins. And through this fabric travels rain. Cosmic rays constantly pass through us from the galaxy, every second. High-energy particles, mostly protons, and atomic nuclei, stream through your body, launched long ago by exploding stars. These are cosmic rays, and they are everywhere. They travel close, to the speed of light, bending through magnetic fields, bouncing off clouds, and occasionally colliding with atoms in Earth's atmosphere, where they create showers of secondary particles. Most of the time, we don't notice them, but they carry stories from across the galaxy, evidence of ancient supernova, traces of distant acceleration, messages from the violent hearts of stars. Even as you rest, even as you sleep, the galaxy is whispering in particles, in silence, in lightless rays, connecting you, physically, to the farthest reaches of the spiral. Let us look at the shape again. Is it perfect? No, the galaxy is not symmetrical. Though many diagrams show it as a neat, even spiral, the Milky Way is not perfectly balanced. One side of the disk appears thicker. Some spiral arms are brighter, longer, or more curved than others. The warp in the outer disk is lopsided. Even the star counts between hemispheres are slightly off. These asymmetries may be caused by gravitational encounters, past mergers, or the influence of dark matter. They remind us that galaxies, like living things, carry traces of their histories in their shapes. Scars of collisions, wrinkles of time, and quirks of uneven growth that give them character and depth. It is a crooked smile in the dark, and that is beautiful. Let us look for the oldest thing. The oldest known star may live in our halo, high above the galactic plane, drifting through the halo. Astronomers discovered a star, or perhaps several, that may be nearly as old as the universe itself. One such star is known as Methuselah. Another has a catalogue number SMSS J0313036670839.3, a long name. For an ancient soul, it contains almost no heavy elements, a signature of stars born soon after the Big Bang, before generations of supernovae enriched the cosmos. It likely formed over 13 billion years ago. Long before the Milky Way was fully formed, it burns quietly now, with a soft, red glow, low in mass, but rich in history. It is not just a star, it is a time capsule, a living relic from the universe's earliest dawn, still shining, still watching. Let us return to the spinning wheel. The center of the galaxy spins faster than the outskirts. In the inner regions of the Milky Way, stars orbit the center. Much more rapidly than those farther out. Near the core, the gravitational pull is stronger, packed with mass from stars, dust, and the supermassive black hole, Sagittarius A. This causes stars to sweep through tighter, faster orbits, completing revolutions in just a few million years, out in the suburbs of the galaxy. Like where our sun lives, stars orbit more slowly, taking hundreds of millions of years. This uneven rotation creates twisting patterns, stretches spiral arms, and keeps the disk from behaving like a solid structure. The galaxy moves like a great wheel, but one whose rim lags behind its core, creating the spiral shape we know so well. And these arms are shaped by density waves. We touched on this before, but let us deepen the understanding. The spiral arms of the Milky Way are not fixed trails. They are patterns, like sound waves moving through air, or ripples moving through water. As gas and dust pass through these waves, they are compressed, triggering star formation, lighting up the arms with bright young stars. These stars eventually drift out of the wave, while new ones form behind them, creating a self-sustaining illusion of structure, like ripples in a pond, or traffic clumping on a highway. The arms are dynamic, always in motion. From a distance, they appear still. From within, they are a dance of matter and rhythm, shaped by gravity and time. And what comes from this compression? Birth. Stars are born from cold, collapsing gas. In the dark arms of the Milky Way, star formation begins in silence. Massive clouds of molecular hydrogen, sometimes hundreds of light years wide, drift through space, chilled to just a few degrees above absolute zero. Within these clouds, gravity slowly takes hold. Small regions grow denser and begin to collapse under their own weight. As the gas falls inward, it heats, spins, and flattens, forming a protostar at the center. Over time, the pressure and temperature grow until nuclear fusion ignites, and a new star is born. From the coldest shadows come the brightest lights, spun gently into being by the quiet force of gravity. But families do not always last. Star clusters can dissolve into the galactic field. Many stars are born not in isolation, but in groups, tight clusters, formed from the same collapsing gas cloud. These clusters, bound by mutual gravity, drift together for millions or even billions of years. But over time, they begin to scatter. Tidal forces from the Milky Way's mass, close encounters with other stars, and internal dynamics all work to pull clusters apart. Stars peel away, one by one, until the cluster fades into the general starfield of the galaxy. Even our Sun was likely born in a stellar cluster long ago, its siblings now scattered, dimmed, or lost in the haze of distance. We drift alone now, but we began together. Let us drift deeper into the chemical heart of the spiral. There are stars that act as fossils. The galaxy contains ancient, hyper-metal poor stars. Among the rarest and most precious objects in the Milky Way are these faint, old suns. Stars whose atmospheres contain almost no elements, heavier than helium. Some of these contain less than 1/10,000th the iron found in the Sun. Imagine that purity. These stars are believed to be among the firstborn, the second generation perhaps, born after the very first supernovae of the very first stars, carrying only faint traces of enrichment. From a universe still forming itself, they are incredibly old, incredibly pure, and scattered in the halo like distant lanterns from the dawn of time. Each one is a kind of relic, a glowing, gravitationally bound signature from a near-forgotten epoch, when the universe was simple and the galaxy was young, but complexity arose quickly. Planetary systems form throughout the Milky Way. Planets are not a rare feature of the cosmos. They are a natural consequence of star formation. As a new star ignites, a rotating disk of leftover gas and dust surrounds it. Within this disk, particles stick together, gather mass, and grow into worlds. Across the Milky Way, planetary systems are common. Some are vast, with gas giants and frozen moons. Others are compact, with rocky planets hugging close to dim stars. Some may resemble our own, while others defy our expectations entirely. Planets made of diamond, planets where it rains glass, planets orbiting two suns. The galaxy is not just full of stars, it is full of systems, solar families, each one with its own unique balance, orbit, and potential. Billions of stages waiting for players. Where are we in this vast theater? Earth is near. The co-rotation radius. In the Milky Way, the spiral arms rotate at a different speed than individual stars, like a moving pattern, rather than a solid structure. But there is a special distance from the center, called the co-rotation radius, where the average speed of stars matches the rotation speed of the spiral arms themselves. Earth's sun orbits close to this boundary. This gentle match in motion may help us. It may allow us to stay between the arms for longer periods, avoiding frequent crossings of spiral arms, places with higher star density, more supernovae, and gravitational disturbances. We live, quite possibly, in a more stable neighborhood of the galaxy, shielded not by walls, but by resonance, by the perfect timing of our orbit. But our orbit is not flat. The sun bobs up and down through the galactic plane as it orbits the Milky Way. The sun doesn't follow a perfectly flat path. Instead, it moves in a gentle wave, drifting above and below the galactic plane, like a cork in slow motion, rising and falling over tens of millions of years. This vertical oscillation is caused by the gravitational tug of the galaxy's mass, pulling the sun back when it gets too high, releasing it as it passes through. Some researchers have even wondered whether this motion might influence cycles of extinction on Earth. Perhaps passing through the dense disk exposes us to more cosmic rays, or disturbs comets in the Oort cloud. Though the evidence is not yet clear, still it's a reminder. Even on its steady path around the center, the sun is not gliding, it's swaying softly through space, dancing to the gravity of the disk. And speaking of gravity, we return to the ghost. We don't know what dark matter is, but we know it's there. Dark matter makes up most of the Milky Way's mass, yet it has never been seen directly. It does not emit or absorb light. It passes through ordinary matter, as if it weren't there, but its gravitational effects are unmistakable. It holds the galaxy together, explains the unexpected rotation speeds of stars, and shapes the formation of large-scale cosmic structures. Without it, the Milky Way would fly apart. Astronomers detect it, not by seeing it, but by watching how it moves other things. It is the galaxy's hidden scaffolding. Invisible, silent, and still one of the greatest mysteries in science. A riddle wrapping the galaxy in its arms. And because of this, mass is distributed strangely. There's more mass outside the disk than inside. Most of the Milky Way's visible stars lie within the flat, luminous disk. but the majority of its mass resides elsewhere. The galaxy is surrounded by an enormous, dark matter halo, extending far beyond the furthest stars. This halo holds the galaxy together, outweighing the disk by a large margin. It is populated sparsely with ancient stars and globular clusters, but its true bulk is unseen. When we think of the Milky Way, we picture its spiral arms and starry plane. But that's only the glowing surface. The mass that defines the galaxy, its gravity, its motion, its reach, is mostly hidden, enveloping everything. Like a quiet shroud, we are the tip of the iceberg, floating in a dark sea. Let us look back to the center. The Milky Way's core may have flared as a quasar. Today, the heart of our galaxy appears quiet. Sagittarius A slumbers. But there is evidence that it was once dramatically more active. The presence of huge gamma-ray structures like the Fermi bubbles and traces of high-energy light reflected in surrounding clouds suggest that the supermassive black hole at the center may have once flared as a quasar or a ciphered nucleus, a brilliant, violent beacon fueled by infilling matter. Quasars are among the brightest objects in the universe, outshining entire galaxies. If the Milky Way once burned like this, it would have looked dramatically different. A spiral wrapped around a blinding heart of light. That time has passed. The fire has dimmed, but the echoes remain, rippling outward into the halo. And change is constant. The galaxy's structure changes over billions of years. Galaxies may look timeless, but they are always evolving. Spiral arms shift, bars form and dissolve, gas flows inward and outward, stars are born and die, leaving behind a changing population. Even the shape of the Milky Way's disk, warped, rippling, and lopsided, is slowly altering. Encounters with dwarf galaxies and dark matter can bend or twist the structure. Over billions of years, the galaxy's silhouette has shifted like a drifting cloud. The Milky Way of today is not the one that was, and not the one that will be. Its beauty lies not in permanence, but in quiet transformation, a slow metamorphosis of light, and from far away, ripples arrive. Gravitational waves ripple through the galaxy from distant mergers. All across the universe, massive objects collide. Black holes spiral together, neutron stars crash, and entire galaxies merge. These events send out gravitational waves, ripples in the fabric of space-time itself. Though faint, some of these waves pass through the Milky Way, distorting space by tiny amounts as they travel. They are incredibly difficult to detect. But observatories, like LIGO and Virgo, have already captured several. New experiments aim to detect the background hum of gravitational waves that fills the cosmos. Even now, as you rest, space itself is shifting, stretching, compressing. Not enough to feel, but enough to tell us that somewhere far away, the universe is changing, and we are feeling the tremor. Let us look at the wanderers again. Some stars orbit in elongated, tilted paths. Not all stars move in neat circles around the galactic center. Some follow long, stretched ellipses, their paths looping high above and far below the disk, tilted at odd angles from the main plane. These stars likely come from different origins. Relics of dwarf galaxies swallowed by the Milky Way, or survivors of ancient gravitational upheavals. Their orbits are clues, three-dimensional maps of the galaxy's chaotic past. By tracing their motion, astronomers reconstruct the invisible architecture of the Milky Way's mass and memory. These stars drift like messengers from disrupted systems, tilted, stretched, but still bound to the whole. And there are particles, ghosts, passing through us. The Milky Way emits neutrinos we can barely detect. Every second, trillions of neutrinos pass through your body, straight from the stars. These ghostly particles are produced in nuclear reactions, from the sun, from supernovae, and from cosmic rays striking atoms in space. The Milky Way is bathed in them, yet they are so light, so unreactive, that they slip through almost everything, leaving no trace. They pass through the Earth as easily as light passes through glass. Special observatories buried deep underground, or under ice in Antarctica, try to catch just a few flashes of light from a rare collision. Neutrinos carry information from places we cannot see, from stellar cores, collapsing giants, and the galaxy's unseen energy. They are the whispers of cosmic fire, speaking a language of pure physics, and the medium they travel through is not empty. Interstellar space isn't empty, it's a turbulent sea. Between the stars, space is not smooth or still. The interstellar medium, thin clouds of gas and dust, is stirred by shock waves, magnetic fields, and the motion of stars. Temperature can vary wildly, from millions of degrees near a supernova to nearly absolute zero in a molecular cloud. Flows of material collide, mix and fragment. Clouds stretch, fold, and tumble. On large scales, this creates a kind of turbulence, like a slow-motion ocean swirling through the disk. Star formation, cosmic rays, and even galactic evolution are all affected by this restless sea. What looks from afar like calm starlight is up close a dynamic, rippling fabric, shaped by invisible winds and ancient energy. And within this sea there are orphans. The galactic halo may contain rogue planets. Planets are not always tethered to stars. Some form normally and are later ejected from their systems. Others may never have had a star at all, forming directly from collapsing gas clouds. These are rogue planets, worlds adrift in the galaxy, cold, dark, and alone. Though difficult to detect, studies suggest that there may be billions of them in the Milky Way, some even in the outer halo, where stars are few and far between. Without light or warmth, they float unseen, warmed only by internal heat. They are orphans of the galaxy, planetary drifters following long, lonely paths through the darkness between stars. Silent worlds with no sunrises and no sunsets, only the eternal, starry night. And helping guide this night are fields. Magnetic fields shape the flow of cosmic dust, interstellar dust. Tiny grains of carbon and silicate moves not just under gravity, but also under the influence of the galaxy's magnetic field. These fields thread through the Milky Way like invisible currents, guiding the motion of charged particles and influencing how gas and dust align. In some regions, dust grains spin rapidly, emitting faint microwave light. In others, they align with magnetic lines, polarizing the starlight that passes through them. Understanding these effects helps astronomers trace the magnetic field structure and even remove its influence from cosmic background studies. Dust is not passive. It dances to a magnetic rhythm, following hidden patterns in the dark, aligned by forces we cannot see. But matter is also made. Some stars are enriched by neutron-star collisions. When two neutron stars, the ultra-dense cores of dead stars, spiral together and collide. They create one of the most violent events in the universe, a kilonova. In this brief, blinding explosion, enormous quantities of heavy elements are forged: gold, uranium, and more. These materials are cast into space, mixing with gas, and eventually forming new stars. Some stars in the Milky Way carry the chemical fingerprints of these rare events, enriched in elements that could only have come from such collisions. They are not just luminous bodies, but record keepers of ancient cataclysms, burning with the residue of stellar wreckage and cosmic alchemy. The gold ring on your finger, it was likely forged in such a fire long before the Earth was born. Let us peer into the very center again. The Milky Way may have a hidden bar within a bar. At the heart of the galaxy lies a bar of stars, an elongated bridge of light crossing the central bulge. But deep within that bar, astronomers have found hints of another, smaller bar, tilted at a different angle, rotating independently. This inner structure is difficult to see directly, obscured by dust and distance, but its gravitational influence appears in the motion of nearby stars and gas. Bars like this may help funnel material toward the supermassive black hole, feeding it and shaping the dynamics of the core. The Milky Way's center is not one simple shape. It's a layered, shifting labyrinth of light and motion, wheels within wheels, bars within bars, turning in the deep dark, and the galaxy breathes. Gas inflows feed the galaxy from the cosmic web. The Milky Way is not a closed system. It draws in fresh gas from the intergalactic medium. Long, tenuous streams flowing through the vast cosmic web. These inflows provide the raw material for new stars, replenishing what the galaxy loses over time. Some gas arrives as cold filaments, slipping quietly into the disk. Other streams fall in hotter, shock-heated forms, lighting up in ultraviolet or X-ray light. These invisible rivers sustain the galaxy's growth and evolution, linking it to the larger universe beyond. Even now, the Milky Way drinks from distant reservoirs, nourished by threads of matter spun from the early cosmos, connecting us to the great structure of the universe. And it exhales too. Hot gas bubbles form chimneys out of the disk. When clusters of massive stars go supernova, they create enormous cavities in the interstellar medium. These can join together into superbubbles, vast pockets of hot gas that punch upward through the galactic disk and vent into the halo. The result is a kind of chimney, a channel where energy, gas, and magnetic fields escape from the plane of the galaxy. These chimneys regulate the pressure of the interstellar medium, redistribute metals, and help shape the halo structure. The galaxy, in this way, breathes, not just within the disk, but through towering columns that carry its energy up and out into the dark, a vertical wind blowing from the stars. And the light is not always gentle. The galaxy shines in X-rays from old stars and black holes. Though the Milky Way appears calm in visible light, it glows fiercely in other wavelengths. X-rays pour from its core, from collapsed stars, and from the edges of black holes. White dwarfs and neutron stars in binary systems can siphon matter from companions, heating it to millions of degrees. Hot gas in the halo also emits faint X-rays, revealing the galaxy's larger skeleton. We cannot see this high-energy light with our eyes, but telescopes like Chandra and XNM Newton paint a very different portrait of the galaxy. Not a tranquil spiral, but a realm of extreme temperatures, compact remnants, and hidden radiation, a place of power masked by distance. Let us listen now to the rhythm of the deep. Pulsars act as cosmic clocks throughout the Milky Way. When a massive star dies and collapses into a neutron star, it may be left spinning, fast and precise, with beams of radiation sweeping across space, like the light of a lighthouse. Turning in the night, these are pulsars, and some rotate hundreds of times per second, pulsing in regular, measurable rhythms. They are so consistent that astronomers use them as cosmic timekeepers, tracking their signals to measure distances, test gravity, and even search for gravitational waves. Across the Milky Way, pulsars blink quietly, remnants of death, but also beacons of astonishing order. They keep time not for minutes or days, but for entire epochs, ticking steadily in the silence between stars. Imagine them scattered through the spiral arms, little spinning tops of immense density, keeping the beat of the galaxy's long song and helping us to see the invisible. Radio waves map the hidden structure of the galaxy. Much of the Milky Way is invisible in visible light, hidden by dust, distance, or faintness. But radio waves can slip through these barriers, revealing structures otherwise unseen. They trace cold hydrogen gas, outline magnetic fields, and highlight emissions from pulsars, supernova remnants, and even distant quasars beyond the galaxy. Using arrays of radio telescopes, astronomers have mapped the spiral arms, measured the warp of the disk, and discovered star-forming regions cloaked in darkness. Where light is blocked, radio soundings let us see. The galaxy speaks in a language we can't hear, but one that science has learned to translate into shape and shadow, into maps of the unseen. Let us return to the beginning. The Sun was likely born in a stellar cluster. Stars rarely form in solitude. They are usually born in groups, stellar clusters, shaped from the same collapsing cloud of gas and dust. Our Sun was almost certainly one of these. Long ago, it shared space with hundreds, perhaps thousands, of sibling stars, all born in the same cradle. Over time, gravitational tides, passing stars, and the motion of the galaxy scattered the cluster. Most of the Sun's siblings have wandered far, flung into different orbits, carrying with them traces of our shared past. Some may still shine nearby, invisible among the stars, lost family in a sea of light. We are orphans of a dissolved family, drifting alone but connected by history, and we are looking for them. The Sun's siblings are scattered across the galaxy. Though the Sun's birth cluster has long since dissolved, astronomers are searching for its lost siblings. Stars that share its age, motion, and chemical fingerprint. Using vast surveys like Gaia and spectroscopic databases, researchers hope to identify these long-lost relatives. A few candidates have emerged. Stars that may have shared our origin, formed from the same cloud of enriched gas. If found, they could reveal details about the conditions in which the Sun and the early solar system were born. Our place in the galaxy is not entirely solitary. Somewhere out there, the Sun's ancient kin may still shine. Perhaps one day we will find them and know where we truly came from. But the ground beneath us is not steady. The galactic disk wobbles as it spins. The Milky Way's disk is not perfectly flat. It wobbles gently, rippling like a spinning plate nudged off balance. This warp is most visible in the outer regions, where the disk bends upward on one side and downward on the other. It may be caused by the gravitational influence of nearby dwarf galaxies, interactions with dark matter, or internal asymmetries. The wobble rotates slowly, like a vast wave moving through the stars. From Earth, we don't feel it. But from afar, the Milky Way is not a pristine spiral. It is a breathing, undulating sheet of stars, curving gently as it turns, like a leaf caught in a stream, or a dancer's skirt in motion. And this motion creates tides. Galactic tides can distort star clusters and streams. Just as the moon's gravity pulls tides on Earth, the immense mass of the Milky Way exerts tidal forces on everything within it. Star clusters, satellite galaxies, and even globular groups feel the galaxy's uneven gravitational pull. Over time, these tides can stretch and distort them, drawing out long stellar streams, or peeling stars away from their orbits. Many of the faint arcs of stars mapped across the sky are remnants of such encounters, clusters in the process of being unraveled. Galaxies slowly torn apart. The galaxy doesn't break these structures suddenly. It unravels them patiently, strand by strand, over millions of years, like a gentle cosmic erosion, wearing down the old to build the new. But how heavy is it? The Milky Way's mass is still uncertain. You might think we would know the mass of our own galaxy, but measuring it is remarkably difficult. Stars and gas make up only a small portion of the total. The rest lies in the vast dark matter halo, which we cannot see directly. Estimates vary. Some suggest a mass close to 1 trillion times that of the Sun. Others place it much higher, perhaps 1.5 trillion. The uncertainty comes from trying to measure how fast stars orbit at great distances, a task clouded by limited data and the influence of invisible matter. The Milky Way is our home, but its weight remains a quiet mystery, a question mark hanging in the dark, and it may be heavier than we thought. It may be heavier than Andromeda. For many years, astronomers assumed that the Andromeda galaxy, slightly larger and brighter than the Milky Way, was also more massive. But recent measurements suggest that the Milky Way's dark matter halo may be broader and denser than previously believed. If that's true, our galaxy could outweigh Andromeda, despite its more modest appearance. This matters not only for comparisons, but for predictions. When the two galaxies eventually merge, their relative masses will shape the encounter's dynamics. The Milky Way may look gentle, but beneath its quiet spiral arms, it carries more weight than we once imagined. Hidden muscle in the dark, and visitors are arriving. The Magellanic Clouds may be on their first orbit. The Large and Small Magellanic Clouds, two bright satellite galaxies visible from the southern hemisphere, have long been thought to orbit the Milky Way, like moons. But new evidence suggests they may be newcomers, captured only recently in cosmic terms. Their velocity and motion through space hint that this could be their first close pass. If true, they're not long-standing companions, but distant wanderers just now falling under the Milky Way's pull. Their arrival has stirred the outer disk and warped the galaxy's shape, as if the Milky Way is responding to a new gravitational guest. The sky, quiet as it seems, is full of first encounters, meetings that take billions of years to unfold, and they leave a trail. The Magellanic Stream is a ribbon of stripped gas. Trailing behind the Magellanic Clouds is a vast ribbon of hydrogen gas. a structure called the Magellanic Stream. It stretches over hundreds of thousands of light years, wrapped in curves and arcs across the southern sky. This stream was pulled away by tidal forces. As the dwarf galaxies passed close to one another and to the Milky Way, invisible light, it reveals itself in radio wavelengths, a long, trailing whisper of motion and loss. The stream may one day feed new star formation in the Milky Way, or settle into the halo like a thread of memory stretching between galaxies, connecting the visitor to the host. And not everything is flat. Some gas clouds orbit in polar directions. Not everything in the Milky Way follows the neat plane of the disk. Some clouds of gas, and even some stars, move in highly inclined orbits, passing above and below the galaxy's main structure. These polar orbits likely come from past mergers, when dwarf galaxies or stray clouds were captured at odd angles. Over time, they continued to orbit on tilted paths, like comets around a planet. These misaligned orbits are records of disruption, visible reminders that the galaxy is not a closed system, but an evolving structure, shaped by the unpredictable flow of cosmic history. Things come from all directions and leave their mark in the geometry of the spiral. And the past explodes. Giant shells of gas surround past starbursts. In several regions of the Milky Way, astronomers have found enormous spherical shells of gas, some spanning hundreds of light years. These shells are the remnants of powerful starbursts, episodes when clusters of massive stars formed together, lived brief lives, and exploded in rapid succession. Their combined winds and supernova carved out huge cavities in the interstellar medium, blowing gas outward in all directions. Over time, the expansion slows, but the shells remain, ghostly bubbles marking where the galaxy once burned bright with stellar birth and death. These are the fossils of cosmic fireworks, still echoing in the cold. Silent rings expanding forever. And sometimes stars touch. Stars occasionally collide in dense regions. Space is vast, and stars are small. But in the densest regions of the Milky Way, such as the cores of globular clusters, stars can pass close enough to interact and even collide. When they do, the result can be dramatic, a burst of light, the merging of two suns, or the formation of a rare blue straggler star, one that appears younger than its neighbors, because it has stolen mass and fuel. These collisions are rare, but not impossible. Over billions of years, the tightest stellar neighborhoods can rearrange themselves through gravity and chance. In these crowded stellar cities, time moves differently, and space is never quite empty, and partnerships break. Binary stars can be torn apart by tidal forces. Many stars live in pairs, orbiting each other in gravitational embrace. But even this bond can be broken if a binary system passes close to the Milky Way's central black hole, or through a dense cluster. Tidal forces can disrupt their orbit, flinging one star away while the other is captured or slowed. In some cases, a companion is hurled out of the galaxy entirely, becoming a rogue star, speeding through intergalactic space. These stellar breakups happen silently, in places we rarely see. A quiet tearing of ancient partnerships by gravity's indifferent hand, leaving one star alone, and the other lost in the dark. And some leave forever. Some stars escape the galaxy entirely. Most stars are gravitationally bound to the Milky Way, but occasionally a star reaches escape velocity, over 500 kilometers per second, and is flung outward, never to return. These hypervelocity stars are rare but real. Some are thought to be ejected by interactions with the supermassive black hole at the galaxy's center. Others may be slingshotted by three-body encounters or supernova in binary systems. Once free, they travel alone into intergalactic space, tiny lighthouses drifting far beyond the spiral's edge. They carry the galaxy's memory outward, becoming solitary pilgrims in the great dark between galaxies. Messengers sent into the void. But strangers arrive too. The Milky Way contains stars from other galaxies. Not all stars within the Milky Way were born here. Some may have originated in other galaxies, captured during mergers, or flung into our halo from distant regions of the local group. These intergalactic wanderers often move on unusual orbits, far from the disk, tracing paths through the outskirts or halo. They can be identified by their composition or motion. Stars that don't quite fit the local patterns. Like cosmic immigrants, they bring stories from other environments, other histories, other skies. The Milky Way is not a sealed system. It is a living mosaic, slowly stitched together by time and motion, a collection of lights from many different homes. And the gas moves too, a fountain of gas, cycling between the disk and halo. Above and below the Milky Way's bright disk, gas rises and falls in a quiet loop known as the galactic fountain. Supernovae and stellar winds heat and eject material upward into the halo, where it cools, condenses, and gently rains back down over millions of years. This cycle stirs the interstellar medium, redistributes heavy elements, and helps regulate star formation. It's a quiet respiration, a breathing motion of matter between the dense plane and the vast halo. The galaxy, in this way, doesn't just spin, it circulates. It exhales and inhales, keeping its structure in motion across immense spans of time. A slow, vertical heartbeat. And in the dust, there is potential. The galaxy's dust grains carry organic compounds. Within the clouds of interstellar dust that drift between stars, scientists have detected complex organic molecules, carbon-based compounds that form the raw ingredients for life. These include polycyclic aromatic hydrocarbons, simple sugars, alcohols, and more. Though not alive, they are chemically rich, formed in the atmospheres of dying stars, or within cold clouds shaped by radiation. These tiny grains, carried across light years by galactic winds, settle into the gas that forms stars and planets. Some may have fallen onto the early Earth. The galaxy's dust is not just debris. It is a cargo of potential, drifting silently through the dark, waiting for a planet to land on. Interstellar clouds may seed solar systems with ingredients for life. The birthplaces of stars are also the birthplaces of worlds. As planetary systems form from collapsing clouds of gas and dust, they inherit the chemical fingerprints of their parent nebula. If that cloud contains water, carbon compounds, and other building blocks of biology, those ingredients may end up in comets, asteroids, or planets. Some regions of the Milky Way are especially rich in such prebiotic chemistry. We don't yet know how common life is, but the conditions for it seem to arise naturally. The seeds of life may be scattered far and wide, tucked into the galaxy's coldest cradles, waiting for a place to grow. And some stars spin like tops, Some stars rotate hundreds of times faster than the Sun. Most stars spin, but some spin incredibly fast, completing a full rotation in just a few hours. These rapid rotators are often young, massive, and unstable, with equators that bulge from centrifugal force. A few reach such high speeds that they fling off material, forming glowing disks around themselves. The Sun rotates once every 25 to 35 days, depending on latitude. But these fast, spinning stars rotate hundreds of times more quickly, approaching physical limits. Their internal structures and evolutionary paths are different. Their lives may be brief, but while they last, they spin like sirens in the dark, calling out with light and speed. And finally, our angle. The galaxy is tilted relative to the ecliptic. From Earth, the Milky Way arcs across the night sky in a graceful band of light. But it doesn't align with the plane of our solar system, the galactic plane, the flat disk in which most of the galaxy's stars reside, is tilted about 60 degrees relative to the ecliptic, the path traced by the Sun and planets. This tilt is why the Milky Way rises at an angle, and why it shifts position with the seasons. We are part of the galaxy, but our own little system is angled slightly askew, a small, tilted boat, drifting through a larger, spinning sea of stars, listing gently as we sail through the dark. Let us look back one more time at the oldest lights. Some stellar remnants are older than the galaxy's disk. Among the faint stars in the halo, astronomers have found white dwarfs, the cooling cores of once luminous stars, that are older than the Milky Way's thin disk itself. These ancient remnants formed when the galaxy was young, before its main structure had fully settled. Their existence hints at an earlier time of star formation, a deeper history. Etched into the outer halo, they have burned for billions of years, slowly fading, carrying with them the quiet residue of a time when the Milky Way was still gathering its shape. The disk may be bright, but the halo remembers further back. It holds the ashes of the first fires, and the galaxy reaches far. The farthest stars orbit well beyond the main structure. The Milky Way's most distant stars orbit far beyond the familiar spiral arms, tens or even hundreds of thousands of light years from the center. These stars move through the galactic halo on slow, wide paths, taking billions of years to complete a single orbit. Many were likely captured from smaller galaxies in past mergers, now drifting in the outermost reaches. Like distant sentinels or border guards, they are faint, sparse, and far between, but they help define the galaxy's size, shape, and gravitational influence. The Milky Way is not just what we see. It extends deep into the dark, shaped by wanderers at its edge, marking the boundary where home ends and the void begins. And the shape is unique. The Milky Way's shape is lopsided in several ways. Though often pictured as a symmetric spiral, the Milky Way is subtly lopsided. One side of the disk appears thicker. Some spiral arms are uneven in brightness and extent. Even the stellar halo is slightly off-center. These asymmetries likely arise from gravitational interactions with the Magellanic Clouds, with dark matter clumps, or with past mergers. The galaxy is not a perfect pinwheel. It is a living structure, marked by tugs and twists, like a spinning dancer whose skirt has been caught by the wind. Its beauty lies in that irregularity, a graceful imbalance sculpted by time and motion and we measure it with blinking lights. Astronomers map the galaxy using variable stars. Certain stars pulse in brightness over regular intervals, expanding and contracting like slow, luminous heartbeats. These are variable stars. And some types, like Cepheids and Lyrae, have well-known relationships between their brightness and their pulse period. By measuring how long a star takes to brighten and dim, astronomers can determine its true luminosity. And by comparing that to how bright it appears, its distance. These stars serve as cosmic yardsticks, helping us map the shape, structure, and scale of the Milky Way. They are lights that measure the dark, blinking beacons scattered through the spiral, guiding us through the vastness. And now we have a new map. The Gaia mission is revolutionizing our understanding of the Milky Way. Launched by the European Space Agency, the Gaia spacecraft is creating the most precise map of the Milky Way ever made. By measuring the positions, motions, and brightness of over 2 billion stars, Gaia reveals the galaxy's three-dimensional structure and its motion through time. It has uncovered streams from shredded galaxies, mapped the warp of the disk, and traced the sun's orbit with exquisite detail. With each new data release, Gaia deepens our understanding, turning a hazy smear of stars into a sharp living map. It is astronomy's most ambitious star chart, a quiet revolution unfolding among the stars, giving us eyes to see the motion of billions of years. Let us look down the road. The galactic plane marks a dense path of stars. If you look up on a dark night, away from city lights, you may see a hazy river of starlight crossing the sky. That's the galactic plane, the thickest slice of the Milky Way's disk. It's not a line, but a depth, a vast, flattened band where the majority of the galaxy's stars reside. Through this plane, stars are densely packed, dust is layered, and star formation is common. From our vantage point, we're looking along the grain of the galaxy, peering through its richest corridors. This band isn't just beautiful. It's the crowded, humming heart of where most stars live and die. A thoroughfare of light, cutting through the dark. And the brightest part is hidden. The night sky is brightest toward the galactic center. The core of the Milky Way lies in the direction of the constellation Sagittarius, a rich, glowing concentration of stars, dust, and unseen mass. From Earth, we can't see the very center. Invisible light. Dust clouds obscure our view. But the area glows with brightness in infrared and radio. Even with the naked eye, the region appears more crowded, more luminous, filled with the overlapping light of billions of stars. We orbit far from this center, in a quiet suburb of the galactic disk. But when we look inward, we glimpse the crowded city at the galaxy's heart, the downtown of our cosmic metropolis, aglow with ancient fire, and our view is constrained. We see the Milky Way edge on from Earth. Because we live within it, we cannot look down on the Milky Way from above. Instead, we see it from the inside, a flat ribbon of stars stretching across the sky, curved only by the horizon. This edge-on view compresses the galaxy into a single arc, making it hard to grasp its full structure from our perspective. It took centuries of observation, cataloging, and mathematical deduction to realize the spiral we belong to. From Earth, we gaze through its disk, like standing in a forest and looking along the line of the trees. We do not see the shape we're part of. only the vastness that surrounds us. We are the eye, trying to see its own face. And there is so much more. The galaxy holds far more than we can ever possibly see. Even with our most sensitive instruments, we glimpse only a fraction of what the Milky Way contains. Light is blocked by dust. Motion is hidden in silence. Dark matter outnumbers luminous stars. Between every star lies emptiness, and within every empty space, potential. The Milky Way is not just what we see, it is what we suspect, what we infer, what we long to understand. It holds ancient light, future stars, drifting worlds, and questions still without answers. And within that vastness, somehow we find ourselves, one planet among many, orbiting a quiet star, floating through a story, too wide for the eye. And now the stars begin to dim behind your thoughts. We've drifted through 100 quiet truths, from the warp of the galaxy's disk to the farthest halo stars, from newborn suns to long dead remnants, from dust and gas to light and shadow and everything in between. You've wandered through stellar nurseries, danced along spiral arms, and gazed toward the galactic heart glowing behind curtains of dust. You are a part of this galaxy, not just a passenger on Earth, but a participant in its long and luminous unfolding. The iron in your blood was forged in stars. The oxygen you breathe was sculpted in ancient explosions. The atoms of your body trace their lineage to the earliest times, born from the same matter that now fuels suns and whispers through clouds of interstellar dust. Tonight, as you rest, the galaxy turns on, stars are forming, light is traveling, silent orbits continue, and you are floating within it. A small warmth in the dark, resting in the spiral arm of a quiet, radiant sea. There is nothing left to do. The universe is holding you. Gravity is cradling you. The stars are watching over you. Drift now into the deep velvet silence, into the peace of the ancient spiral. Sleep well and dream softly. Good night.